All right, hello and welcome back to Nick Does Algos. In this lesson, we'll be covering the Hackerrank easy rated algorithm, Flatland space stations. Kind of a funky question, but once you start to understand it, I think you might like it. Essentially, you are keeping track of cities in a country called Flatland. Each city in this country is separated by 1 kilometer. Some cities have space stations and some do not. You want to find the distance between the space station and the cities and return the maximum distance that you encounter. So we'll walk through this explanation down here. It does a good job of describing what's actually going on. So here you have cities numbered from 0 to 4. This city numbered 0 has a space station. This city numbered 1 does not. So for city 0, how far is the nearest space station? Well, it's 0 because the space station occurs inside that city. At city 1, how close is the nearest space station? The nearest space station is 1 away from it. You could compare it to space station 4 way out here, but you wouldn't because you know that there's a closer one. For city 2, city number 2, how far is the nearest space station? Well, you've got a city over here that's 2 away, and a space station over here that's 2 cities away, and a space station over here that's 2 cities away. So you would return 2 for that one. Essentially, you're finding the distance from the city to its closest space state, or you're finding the distance from a city to its 2 closest space stations and keeping track of the minimum of that. And if you kept track of the minimum of that for each city, you would then return the maximum of that array or those distances. So here you would keep track of 1 because city number 1 is 1 away from space station 0. Here you would keep track of 2 because the closest space stations are 2 away. And here you would keep track of 1 again because it's 1 away from the closest space station. So you wind up with this subarray essentially 0, 1, 2, 1, and 0, and you return the max of that. The max of that is 2. So again, you're always finding the closest space station to a city and then keeping track of that for each city, and the city with the furthest closest space station. If you think about that, that makes sense. The furthest closest space station, that is what you will go ahead and return at the end. You would return the 2. So there's one way to do this in which you create essentially a grid that goes from 0, 1, 2, 3, all the way up to n. And then you would find the distances for each city in your city array, and you would compare it to each and every, C is your space stations array. You would compare each and every space station to each and every city, and then you would wind up with another loop inside of it or another loop inside of that, and you would eventually return the minimum, and then you'd return the maximum. But in that scenario, you wind up with an algorithm that has a big O time of, I believe it's n squared. It might even be greater than n squared. I think it is greater than n squared. But it passes most tests. I actually did that variation first, and it passes most tests, but it fails 2 tests in which the numbers get very, very large. So the best way to go about solving this problem is to think of all the scenarios and write some conditional statements based on those scenarios. So we will be using this example here. These are our cities. We've got our space stations. We've got one at city 13, 1, 11, 10, and 6. And our number of cities ranges from 0 to 19, and you have 20 cities. If you were to use this same logic where you have city 0 and city 4, you have 5 cities. Okay, so let's think of some scenarios. Well, if you have C length of 1, if you had one city that you were working with, you would have 2 distances to find, right? Say you only had, let's comment some of this out, see if I do this properly. Nope, didn't work. Um, let's just quickly do that. Close you off and comment you out. Okay. So say we only had city number 13 with a space station at it. What would happen in that instance? Well, you'd compare 13 to the beginning of your city string. So think of the cities. You've got city 0. Oh, not where I meant to type that. Okay, let's move down. Think of your cities. You've got city 0, you've got city 1, you've got city 2, and so on and so forth. And then city 19 and city 20. And right in the middle, you've got space station 13. So it's quite clear. You would find the the furthest city on both sides from the space station. So you would find that one city is 13 away. On this side, this left side, the distance between 0 and 13 is 13. And then over on this side, the distance between the furthest space station, the furthest city and your space station is 7. And you would go ahead and wind up returning 13 because it is the maximum minimum distance, right? The distance between 0 and 13 is your highest distance for any city whose smallest distance is the distance between it and space station 13. Kind of interesting to wrap your head around, but nonetheless, that is what you're actually looking for. So we can go ahead and write some conditional statements for this. And we'll do that in a bit, but let's run through some more scenarios before we actually get to typing all that out. Okay, so that's if you have one space station. That is what you would do. Let's say you had 2 space stations. The first one is at 5, the next one is at 13. Okay, so you would essentially do that same thing again, but slightly differently. So you'd start 0, 1, and then you get to 5. And then you jump a bit more to 13, and then you jump a bit more to 20 again. So here, let's just put a couple numbers in here for some consistency. Or maybe not. Let's go 9, 10. Okay. And add a period there and a period there. Okay. So let's start at city 0. We know that there's going to be a good distance between city 0 and space station 5. Actually, yeah, let's get rid of that. Don't need that. Okay. So we know these are our space stations, and we are looking for the maximum distance between our cities, right? So we know that 0 would be a pretty good bet because the distance between 0 and space station 5 is going to give us 5. And then, of course, we jump to 1. The distance between 1 and 5 would be 4. And you wouldn't keep track of that because the distance between 0 and 5 is greater. Or you could keep track of it, but at the end of the day, you know that 5 is greater, and that's what you're looking for. And then you wind up with some cities between our space stations. And you could compare 5 to 12. But if you compared 5 to 12, the distance between 5 and 12 wouldn't really be valuable to you because 12 is only 1 away from 13. Really what you need to look for is the city that lands right smack in the middle between 5 and 13, which would be what? That would be, distance between these is 8, so you'd add 4, it would be 9. So 9 has a distance of 4 between each of these, which is the greatest you could find, because if you went to 10, what happens at 10? Well, you've got this 5 distance between Space Station 5 and City 10, but the distance between 10 and 13 is 3. And you would take that value because that's the shortest distance between a city and a space station. Remember, we're looking for the maximum minimum distance from a city to its closest space station, right? So evaluating 10 here doesn't really help us. you would find the difference between 5 and 9. So let's go ahead and put some numbers down here again. The distance between 0 and 5 is 5. The distance between, wrong buttons, 5 and 9 is 4. The distance between 9 and 13 is 4. And then the distance between 13 and 20 is 7. So you can see that for 5, we are evaluating the distance between 0 and 5. And then we are evaluating the distance that is halfway between 13 and 5. So you're evaluating 9. And then for 13, you're evaluating, again, the distance that's halfway between 5 and 13. You get 4 again, kind of redundant, but you've got to do it. And then the distance between 13 and the end, 20. And essentially, if you keep adding space stations, that's what you would keep doing. You'd keep having to find the distance between the midpoint of the two space stations, and so on and so forth. So if you have a space station that's on the lower bound, you're going to compare it to city 0. If you have a space station that is not on the lower bound, you would compare it to the space station to the left of it. And we can explain that by adding another city here. Let's add city 15 in here and get rid of all of this. We can get rid of that one. We don't need that one there. So let's quickly do this again. What's the difference between 0 and 5? You've got 5. What's the difference? So 0 is our lower bound, 20 is our upper bound. We have added space station 15. 9 is not a space station. Let's just update this array up here to show you what the space stations that we're working with are. These are our space stations. 9 is what you wind up evaluating, because 9 is the city that is smack in the middle of 5 and 13. So you'd evaluate the distance between space station 5 and city 9, which is 4. And then you start looking at our next space station. And you're no longer evaluating the distance between your next space station and your upper bound, because there's a space station in the middle. Let's remove this 9, or let's go ahead and put the 9 in parentheses to show that it's not a space station. But 13 is a space station. So here you wind up looking at space station 13, which is 4 away from the midpoint of 5 and 9. And then on the right side again, you would do the midpoint between the two space stations, which would wind up being what? It'd be 14, right? So, sorry, I wouldn't put it there. I'd put 14 like this. And the distance between 13 and 14 is 1. So the two closest cities to 13, or furthest cities from 13, would be city 9, which is 4 away, and city 14, which is 1 away. And then you'd go to your space station 15. Let's move this guy over just slightly. And then there'd be a 1 here between 14 and 15. And then there would be a 5 here between 15 and 20. So you wind up with a couple conditions. You wind up with a condition where you have one city. In that case, you just evaluate the city versus the upper bound and the lower bound, and then you compare those two values. You can also have a scenario where you have multiple space stations, in which on the lower bound, the first space station, you compare it to the lower bound and the next closest space station. And then if that space station has a space station on the right of it and the left of it, you've got two space stations, 5 and 15 here, you would compare it to those two space stations. So if you've got a number that's sandwiched between space stations, you would compare it to space stations, and of course half the distance between those. And then for your last space station, you would compare it to the space station before it and to the upper bound of the city range. So I hope that makes sense. I hope it's clear. Really, that's the whole logic that we're going to use to go ahead and solve this problem. So let's go ahead and start to actually get to work. If it helps, I hope it helps. I'll just comment all this out so you can refer back to it. But really do whatever you can to visualize what's going on here. I'm going to head back to Hackerrank for a second just to capture these cities for this example. And yes, of course, I already solved it. I didn't just jump into this unsolved. I wanted to know what I'm talking about before I'm walking everyone through it. Okay, so there we go. There's our example that we'll be working with. And let's now get to work. So first things first, we need to sort our C. Our cities are not in order. Sorry, our space stations are not in order. So if we were to evaluate this city versus this space station and this space station and find the distance between them, well, that's not actually going to get us anywhere. That's not a comparison that's going to benefit us. So first things first, we will c.sort. And in Python, the c.sort function sorts the list in order from least to greatest, which is the order from left to right, just like this that we're working with, so we can leave that as is. We don't need to reverse it or anything. Okay, and we will also create an empty answers array. And this is where we will store the maximum distances, those cities with the greatest distance between the space station and, yeah, the greatest distance between the city and the space station. Okay, and then we will do a loop. We will loop through our space stations and find these distances. So we can write for I in range length of C. Oh, not capital C, lowercase c. We now have to set up our multiple conditions. So as I said, for this first scenario, what is the condition? The condition is if length of C is equal to 1. If there's only one space station that we're evaluating, we can compare the distance between the upper bound and the lower bound and our space station. And for sake of this example and lack of a headache, I'm going to copy over some code that I've already written, and I'll just quickly walk through it. So you're going to take the point, you're going to find where your space station is, right? This is C of I, that gives you the value of where your space station is. And first you'll compare it to the lower bound. The lower bound is always going to be city 0. And if you do it in this manner, you take the absolute value of the difference between them, you're always going to get a positive value, which is really what you're looking for. Oh, I'm sorry, I skipped a step. We need to establish our temporary array. And what our temporary array is going to do is going to find the minimum distances, right? The minimum distances from the city to the closest space station. Essentially saying closest space station is the minimum. So this is really finding the closest space station to any given city. And then we will add that to our temporary array, and then we will evaluate our temporary array and append the maximum value to our actual answer array. Okay, so let's keep going. There's our first scenario. If length of C is equal to 1, we know we're not going to have a scenario where there's no space station. That's just not part of this problem. So we can then just do an else statement. Any other scenario is a scenario where there are multiple space stations in our country, essentially. Okay, so else. What would the first thing we're going to evaluate be? So in this scenario, when we used 5 and 13 and 15, you would take a look at 5. And how would you represent 5? Well, you would represent it as C of 0. So what is C of 0 here? 0 happens when I is equal to 0. So you would say if I is equal to 0, you do some more logic. You do some more appending to your temporary array. And it's very similar to what we did here, right? Here we compare the city to the lower bound and the city to the upper bound. But in this scenario, we are going to compare the city to the lower bound because its closest, or its furthest city on the left side will be the lower bound. And then we would compare, like I mentioned before, the midpoint between our next space station and our current space station. So again, I'm just going to copy and paste some code that was already written, but it follows that logic. I just know with this specific scenario, I'd wind up with multiple typos and it would be a headache finding all the typos over and over again. So we're just going to stick to copy and pasting. But here you go. This is our first scenario, our lower bound and our first space station. Here we're finding the distance between the space station and the lower bound. And then here we are finding the distance between the midpoint of our space station and our next space station. Midpoint is exemplified by this division of 2. And think about it, you wouldn't just use this division sign because you could wind up with a decimal. You need to round down in that scenario. Okay, so there's our first condition. We could then write a conditional statement that would be like if I is greater, 0 is less than I is less than length C, to find the in-betweens, because what's the other scenario we're really worried about? It is the last space station. In this example, we used 15 as the last space station, where you just compare it to the space station before it and the upper bound. So we're just going to go ahead and do an elif for that. Elif I equals length C minus 1, just because we're working with indexes. So you wouldn't go up to city 20, as I mentioned. There are 20 cities, but your last city would be 19, right? Just because of how indexes work. Okay, so you've got length of city minus 1, and then you're essentially going to flip-flop this. No, you can't do that. Hold on, I'll copy and paste it over. All right, here's our code. And here we compare the value of the city to the value of the upper bound. And that in this scenario would be, let's say you're working with space station 15, you're comparing it to your upper bound of 20, you find that distance would be 5. Oh yeah, technically, like I just said, this would be 19 in the scenario of n equals 20, but we're just gonna stick with 20 for convenience sake. Okay, so there's our first scenario, and this second scenario, what's happening? You're comparing your highest I value, the highest I value your encounter, which in this scenario, when C is sorted, 13 will be the last city that we're going to evaluate. So as I mentioned, we need to compare it to the upper bound and the city to the left of it. And how would you identify the city to the left of it? Well, you could do I minus 1. And that's the value you would compare. Okay, so you've got our lower bound comparison and our upper bound comparison. And then for everything else, for every other I in our iterations through our C loop, we would compare the space station we're at with the space station to the right of it, as well as the space station to the left of it. So let's go ahead and copy this logic. You may already know what this is going to look like after having seen the last two. And there you go. We're comparing our current space station to the space station to the right of it, and dividing by 2, we're finding that midpoint. And then we are comparing our space station to the space station to the left of it and finding that midpoint. All right, and then what do we need to do? We need to take a look at our temporary array. So let's go ahead and print our temp, and that's going to give us 2 values each, right? The distance between the space station on the right and the distance between the space station on the left. And you would take the minimum of that, right? Or I think you would take the maximum. Yeah, sorry, you would take the maximum of that. Okay, so you would answer dot append max of temp. And then outside of that loop, you could take a look at your answers array, print ans. Let's go ahead and remove this print. Make sure that yep, there we go. We get all of our temporary maxes being appended to our answer array. And then from here, we would just print the maximum of this, which would be print max of ants. And that's going to give you the value that we're looking for of 6. All right, and that's it really. Let's go ahead and copy and paste this, or actually because of format and Hackerrank format being annoying, we're going to copy and paste this over from my VS Code, which is just off screen. So we'll paste it here. As you can see, it's all the same. We can get rid of this print, just don't need it. And then we can run our code. There you go, we passed both of our sample test cases, and then we can move over to our test cases. And there you go. You can see that that all happened really, really quickly because you're just using one loop here. You're using one loop, so our big O time is really small. In any other scenario, these later test cases are really, really big. So you would wind up with a really big O time, and even just evaluating these test cases would take a long time, and then it would eventually time out. So that's it. I hope you're following. I hope you understood what's going on. I hope it makes sense. If you have any questions at all, please feel free to drop them down in the comments below. If you enjoyed this video, if it helped you out, please go ahead and hit the like button. And we post these questions just about every day. We post these walkthroughs just about every day. So if you're at the point in your career where you are covering algorithms, go ahead and hit subscribe. I'm sure something will pop up eventually that will help you out again. So thanks so much for watching, and hope to see you in the next one.